Elotropic relations. Note, here elotropic means having properties with different values along different axes. 22. But a precise theory nevertheless admits of considerable extension from the above with mu and c regarded as scalar constants. All bodies are strained more or less, and are thereby usually made elotropic, even if they be not naturally elotropic. The force and the flux are not then usually concurrent or identical in direction. But at any point in an elotropic substance there are always, if force and flux be proportional, three mutually perpendicular axes of concurrence, the principal axis. When we have, referring to displacement, d1 equals c1e1, and d2 equals c2e2, and so on. If the c's are the principal permittivities, the e's the corresponding effective components of the electric force, and the d's those of the displacement. If E be parallel to a principal axis, so is D. In general, by compounding the force components, we obtain force E, the actual force, and by compounding the flux components, we obtain D, the displacement, to correspond, which can only concur with E in the above-mentioned special cases if the principal permittivities be all different. But should a pair be equal, then E and D concur in the plane containing the equal permittivities, for the permittivity is the same for any axis in this plane. The energy stored is still half the scalar product of the force and the flux, or half ED, understanding that the scalar product of two vectors, which is the product of their tensors when they concur, is the same multiplied by the cosine of their included angle in the general case. Vector analysis is, I think, most profitably studied in the concrete application to physical questions, for which, indeed, it is specially adapted. Nevertheless, it will be convenient, a little later, to give a short account of the variolemkins of the subject, in order not to have to too frequently interrupt our electromagnetic arguments by mathematical explanations. In the meantime, consider the dielectric medium further. Distinction between absolute and relative permittivity or inductivity. 23. The two quantities c and mu are to be regarded as known data, given over all space, usually absolute constants. But when the simpler properties of the ether are complicated by the presence of matter, then varying in value from place to place in isotropic but heterogeneous substances, or, in case of elotropy, the three principal values must be given, as well as the direction of their axes for every point considered. Keeping to the case of isotropy, the ratio c over c0 and mu over mu0 of the permittivity and inductivity of a body to that of the standard ether are the specific inductive capacities, electric and magnetic respectively, and are mere numerics, of course. They do not express physical properties themselves except in the limited sense of telling us how many times as great something is in one case than in another. This is an important point. It is like the difference between density and specific gravity. It is possible to so choose the electric and magnetic units that mu equal 1 and c equals 1 in ether. Then mu and c in all bodies are mere numerics. But although this system, used by Hertz, has some evident recommendations, I do not think its adoption is desirable, at least at present. I do not see how it is possible for any medium to have less than two physical properties effective in the propagation of waves. If this be admitted, I think it may also be admitted to be desirable to explicitly admit their existence and symbolize them, not as mere numerics, but as physical magnitudes in a wider sense, although their precise interpretation may long remain unknown. If, for example, h be imagined to be the velocity of a substance, then 1/2 mu h squared is its kinetic energy and mu its density. And if E be a torque, then 1 over c, the elastivity is the corresponding coefficient of elasticity, the rigidity, or quasi-rigidity, as the case may be, while c is the coefficient of compliance, or the compliancy, and 1/2 c times E squared is the stored energy of the strain.